let's see, do you want to try going full screen here? Is it already showing full screen? All right, full screen there. Okay, well, it is my pleasure to introduce Mike Fienen. Sorry if I mispronounced that. He is a research hydrologist at the USGS Upper Midwest Water Science Center in Madison, Wisconsin. And he is a distinguished speaker for us today in the Tides of Innovation speaker series here at the Illinois State Water Survey in Champaign-Urbana. Mike uses a diversity of modeling approaches, including statistical and probabilistic modeling, to explore and understand how groundwater issues are related to water availability and a diversity of groundwater research. That's about as much as I prepared, Mike. So with that, I'll be happy to introduce you and let you take it away.
All right, great. So you can hear me okay? Is this all right?
Yeah, that's great. Thanks.
Okay, excellent. Well, thanks so much for the invitation today and for coming to the seminar. As my introduction indicated, I focus a lot on groundwater. And as a research hydrologist at the US Geological Survey, I really am coming from the kind of practical applied research background as opposed to kind of basic fundamental research. So those are two perspectives that I'm bringing to this talk today. So kind of coming from groundwater and coming from applied research. Oops. All right, so, but thinking about groundwater, why do we need groundwater models anyway? What's the point of having a model? And I like to go back to this court case from the Texas Supreme Court in 1904. They used some really colorful language here. And they said that basically the issue was there was a farmer and he had a well, it was producing water, no problem. And the railroad came in. This is back in the days of steam trains when people needed tons of water to run the steam engines. They put in a well and the farmer's well dried up. And so it was obvious to everybody what had happened. It was obvious that there was a connection and that this new stress on the groundwater system impacted this other person. But in law, to show that there was a damage, there needed to be a clear connection and there needed to be a way to quantify a harm or a damage to this farmer. And so they basically, the Supreme Court basically said they can't. That was impossible. And in this colorful language, they said, because the existence, origin, movement, and course of such waters, that's groundwater, and the causes which govern and direct their movements are so secret, occult, and concealed that an attempt to administer any set of legal rules in respect to them would be involved in hopeless uncertainty and would therefore be practically impossible. And actually, this quotation is from another case in Ohio a few years before the Texas Supreme Court adopted it. I had the opportunity to talk to the current Chief Justice of the Texas Supreme Court a few years ago, and he put a little bit of context around this. Occult in particular, at this time, didn't mean Ouija boards and seances and things like that. It really just meant like obscured and not accessible. But the bottom line was everybody knew this was an issue, but nobody could prove what these connections were. And over the last 120 years since this ruling, luckily we've come a long way. We do a better job of measuring groundwater, but also we can use models to do this quantification. However, the hopeless uncertainty we have not completely gotten around. There is still a lot of uncertainty, and we need to somehow cope with that. And we need to somehow incorporate that into how we use models. So this is just a motivation for why we have groundwater models in the first place. But they do go a long way toward dealing with this problem identified a long time ago. But very importantly, groundwater is not some isolated bit of water out in the world. It's connected to the entire water cycle. And people have probably seen since they were children various pictures of the hydrologic cycle or the water cycle. This is recent work by the USGS, and in order to kind of revive this picture, both using some modern graphics, but more importantly, bringing in all the different aspects of the water cycle. So we've got, everything from the climate and precipitation, water falling on land, but importantly, entering into the groundwater system, leaving the groundwater system connected to lakes and streams and the ocean, and also human impacts. There are human impacts all over the place in this picture. And so we're looking at a big integrated system. Groundwater doesn't exist in isolation, nor does surface water. These distinctions are somewhat arbitrary. Really, all of the water is connected. And so any modeling or decision making that we're going to ever implement needs to start to incorporate all of these different aspects. So before I jump into kind of the examples that I wanted to explore today, to look at groundwater and decisions fitting into the human and hydrologic cycle, I just wanted to acknowledge that I'm part of a team here at the groundwater, or at the Upper Midwest Water Science Center. We're called the Groundwater and Watershed Modeling Team. And when I was invited to give this talk, I had some ideas of what I thought would be interesting and hopefully useful. But I also posed the question to the team, and we spent an hour kind of brainstorming on what aspects of hydrologic modeling and climate science would be interesting. And it was a really fruitful and fun discussion. I wish we could have just hit record. I could just play that for you now. It was really wonderful, and I just want to acknowledge all of my colleagues here at the center. But you're stuck with me today, so I'm going to continue. And I want to show so a few examples from my work and a couple examples from other work. But this also represents collaboration and funding from a lot of different sources. Here in Wisconsin, the university, the Department of Natural Resources, the Geological and Natural History Survey. So I'm going to show some other work from New York that was in collaboration with the Department of Environmental Conservation. And then also the US Navy, Northrop Grumman, and a couple consulting companies that I've been collaborating with in some of this work as well. All right, so I would break down, I like threes. So I thought, what are the three key concepts of kind of the future of water and environmental modeling? And I really think this boils down in a lot of ways to integration, uncertainty, and decision support. Integration broadly is kind of recognizing how groundwater, humans, other media of water all interact in a complicated water cycle, also connected with the climate, and how modeling can work with that. Uncertainty, that's the part of the hopeless uncertainty from the Texas Supreme Court that we're still coping with, and that there are ways that we can take advantage of new techniques to work with uncertainty in our models. And then decision support is really recognizing that these things all go together. So part of the integration question is, most of the time, decisions made about water resources are actually secondary. There's probably an ecological or a social or an economic question that's really at hand. And the hydrology is in support of that. So recognizing these three things, how can we make our models more useful for actual decision making by the people that are managing our water resources? So we'll start with integration, and I'm going to build from initially the groundwater perspective, since that's where most of my research lies. And it's just interesting, I've been in the groundwater field for about 30 years now, and it's kind of there have been waves of interest and disinterest over time, but just in the last year, the New York Times kind of picked up the challenge of looking at groundwater resources on a nationwide scale. And they came up with this great viewer. If people haven't seen it, I'd recommend just kind of going through the archives. It was from August of last year. And we'll take a look at a couple of slides of that. But then beyond that, they've done this whole series of water viewers or of data viewers and articles talking about various aspects of how groundwater is fitting into the national picture. And I think that this has motivated even attention at the White House. We were recently contacted by the President's Council of Advisors on Science and Technology. This is a very impressive, smart group of people that advise the president. And some presidents meet with the council regularly, some don't. The current president does. And so they were asking, what are the main issues facing kind of groundwater resources in the country? So I think that there's right now is a great time to be involved in groundwater and looking at how it fits into the bigger picture. So one of the viewers that was in that original New York Times data story was just looking at groundwater level trends over the country. And this is pretty interesting. You can see areas that people familiar with groundwater resources will recognize: the Central Valley, the High Plains, the Mississippi Embayment. These are all areas where we know there are declining groundwater levels, and they're of concern. But what about here? What about Wisconsin? In the last few years, we see blue arrows. This is rising groundwater levels. Is that a good thing? Does that mean that there's not an issue here? And is hydrology really, again, is this hydrologic picture everything that's needed to make decisions, or is there more to it? And that's what we're going to explore next. So if we're thinking about, for example, the question of groundwater sustainability, how much water can out of the ground sustainably? You could look at that map and decide that some places are under great stress. But again, what about the upper Midwest? This is an integrated question, and we need to start thinking in an integrated way. So the example I'll use is, the first example I want to talk about is the Wisconsin Central Sands Lake Study. So this was mandated by the Wisconsin state legislature a few years ago in 2017. And the question they posed was, this is looking at the Central Sands portion of Wisconsin where it's ideal conditions to grow potatoes, other crops, but especially potatoes. But that really depends heavily on using irrigation. And that irrigation almost exclusively comes from groundwater. So there's, as you saw from the map, it doesn't look like there's groundwater stress here. And indeed, you could pump to your heart's content in this area and never run out of groundwater. But the groundwater is connected to lakes and streams. So the real questions become questions of lake levels and stream flow. So what the legislature asked the DNR to do, and then we ended up collaborating with them, was to determine whether existing and potential groundwater withdrawals are causing or are likely to cause significant reduction of navigable lakes water level below its average seasonal levels. So in any good legal environment, there's a lot to unpack here. Words like significant reduction, what's considered significant, what matters? Which of these lakes is even navigable? There's a strict definition for that. What constitutes an average seasonal level, especially in the face of climate change? This is a very difficult question, or a series of questions that we set out to answer, and it required an interdisciplinary integrated team. But just off the bat, nobody cared about what the groundwater levels were. And that's what, originally a groundwater model would tell you about groundwater levels, but it's lakes that were of interest. So we need to integrate lake models with groundwater models just from the beginning here. And we did this at multiple scales. There's a lot to say here. I'm going to kind of go quickly, but we basically created a model that was bounded by major rivers, the Wisconsin, the Plover on the west, the Tomorrow, Wapaka, Fox, Wolf, and Nina Creek to the south. So there's a big regional model here, but it would be cumbersome to also look at these relatively small lakes at the scale of this big model computationally. So we made inset models focused around the lakes at two different scales. One scale just to be able to manipulate groundwater extraction through simulating agriculture, and then a really zoomed in model that's connected in order to be able to look at the actual lake dynamics. And a big question here is looking at management. So if the question is, are groundwater extractions for agriculture causing an impact on the lake, there's a question of, is there a smoking gun? Is there one groundwater well that's really important, or is it really a cumulative impact of many wells pumping at the same time? And so one of the ways that we looked at this was looking at, this is a time series plot here, and the orange level is the lake elevation. So you can see there are some pretty small scale variations due to just like daily weather changes. There's kind of a bigger climate signal. Things got pretty dry for a while and then got wet again. So this is looking at the lake level at the current level of irrigation. And so that is our starting point. We wanted to look at, what if we just systematically simulated each parcel that's irrigated, turning that irrigation off, going back to a natural state? Would there be a recovery in the lake level? And if so, would one well be really responsible for that, or a couple wells, or would you need to look at a much bigger picture? So I'm gonna play this video here where we're gonna look at a bunch of model runs. The lake level here is in Long Lake, and that's covered by a star here. And then every gray parcel here is an actual agricultural parcel that's being irrigated. And so as the parcels turn to blue, we will be running a different model with that parcel returned to a quote unquote natural state. So turning off the irrigation effectively. And we prioritized the closest, just by distance, the closest parcels to be removed first, and then kind of move out, and you'll see in a kind of concentric pattern as we move away from the lake. And then there will be gray lines that show the recovery or the change in the water level in the lake over time. So I'll start this. Oops. There we go. So what you can see is as these individual wells are removed, there is in fact a recovery, but any one of these distances between two curves is pretty subtle. You could look away and look back, and maybe you'll see that there's a little bit more, but it's not like there's a huge jump because of one well. So any one of these has this pretty small change, but in aggregate, you can see a pretty big change, several feet in lake level that the modeling is showing is due to the agricultural pumping. What's also interesting is once you get to some distance from the lake, the lines start to jump up or just bunch up against each other. You actually stop seeing a change. So this is really a function of distance as well. So some proximity around this lake, there is in aggregate a definite impact from agricultural pumping. And once you get far enough away, it's not impacting this lake. It's probably impacting a different one or a stream. But so this kind of shows that there isn't a smoking gun. It's not that simple. So that's integrating the lake hydrology into the groundwater question. But this was part of a bigger study. They also needed to determine what are the actual ecosystem responses. So we've shown that there is change in lake level, but who cares? Does it matter? And does it matter to the ecology? And the ecology was really quantified in two different ways, looking at fish populations and looking at aquatic plants. Does it change the water chemistry of these lakes? And does it have an impact on human uses, mostly recreation? And so, and I won't pretend to know anything about these questions because this was an interdisciplinary team with a whole set of expertise on lake ecology and socioeconomics that we passed our model results onto, and then they were able to run through their own models and come up with sort of a scorecard for each of these lakes. And so this is kind of where this is sort of the end result of all of this work, was showing one of the lakes, Pleasant Lake. This one is pretty rocky shores, relatively deep and kind of steep topography at the edges. On the left is, I'm sorry, on the right, we'll start with, this is the current picture. This is the lake level given the current level of irrigation. And then if we simulated with no irrigation, you can see that the lake level is a little bit higher. And then we have a scorecard here on those four actual outputs that they cared about. And in this case, there's really no measurable impact to most of the lake ecology. However, there is a small recreational impact, and this is actually due to a few rocky shoals that can be hit by water skiers. That's what they were concerned about here. Long Lake has a pretty different picture. This is a lake that's pretty shallow already to start with. The main recreational activity is like shallow canoeing and fishing. That's damaged because sometimes this lake goes almost completely, or areas of it go completely dry. The fish population is damaged in part by the fact that there's a big invasion of terrestrial plants displacing aquatic plants, and this is happening because when the water levels are low, there's just more exposed lakeshore, lake bottom for terrestrial plants. The water chemistry is impacted. So this one is definitely showing that there's a big impact due to the irrigated agriculture. And Plainfield Lake, which is also in the model, is sort of, again, a mixed bag. Recreation, the water levels stay high enough that you could do some recreational boating. There is no measurable fish population in this lake to start with, so there was no change there. Again, invasion of terrestrial plants, but not enough changes to really impact the water chemistry. So the point here is that the groundwater levels do not exist in a vacuum, right? This kind of modeling needs to be integrated to the bigger socioeconomic and ecological questions. Integration. So if we need these kind of models, how do we make them? In the past, people were pretty focused on their media. There were rainfall runoff models that maybe pretty much ignored the groundwater system. There are climate models that probably, don't necessarily do a very good job of representing surface and subsurface water processes. There were groundwater models that pretty much ignored the surface, right? So, and these codes just at the programming level were designed to operate pretty much separately. And so there's been a lot of work. Again, I'm coming kind of from the groundwater perspective. So ModFlow is the tool that I'm the most familiar with. But they're using some community standards that have developed over the last years to be able to create the codes in such a way that it's easier to integrate. It's easier to drive them from an economic model or to connect to an external surface water or water quality model, those kind of things. And the architecture looks a little bit like this. You could think of the ModFlow core as just a model that stands alone. But now on top of that, there's this effort to build kind of an interface layer. It's called an API, an application programming interface. And the idea there then is you should be able to, from another model, take control of ModFlow in this case, run it, get the results, make changes, run it again, sort of in an integrated way. And so now, one example from their work is looking at this tool called ModSyn. And this is importantly in the West, there's a lot more covering groundwater flow than just the water levels themselves. You've got increasing seniority, right? So here is a minimum in-stream flow requirement. That may be a flow requirement due to ecology, or it may be because there's a senior right that has the rights to this water, which means that upstream water must meet this before they get their allocation. Water flows to money in the West, right? And this is how that works. And so you've also got these irrigated parcels. They may have an independent model that determines how much water is needed to grow the crops based on which crops are planted and climate and soil and those things. These are diversions, these red boxes. So water will leave from the surface water model and go to be irrigated onto these based on the demand. All these different aspects are working together in concert, basically behaving as one model. And that's kind of what we mean by integration. It's challenging. You need to have better, software that's available for or able to handle it. You also need to have like the computational resources to run these. It gets very expensive and challenging. All right, so that's kind of the integration piece, but I said that we would move into uncertainty, and there's really two aspects of uncertainty that I want to cover. One of those is if you have a single model, we know that it's not perfect. We know that the data aren't perfect. The parameters that drive the model are not perfectly known. There's uncertainty there. So how can we put that all into a framework where we use and understand levels of that uncertainty when in the model out forecasts? And so I'll look at an example here. This is a pretty simple example, actually, from upstate New York, this place called the Never Sink Basin. This is pretty steep topography and bedrock with these glacial fill aquifers along the river corridors. And all of these circles are public supply wells. And they have a very simple question. It's a classic groundwater question, which is, where on the surface does water enter the ground and end up at these wells? Because they want to protect the water quality of these water supply wells. So maybe they would impact some kind of restrictions or zoning on things like landfills or other potential contamination sources. And so they want to know where to do this. But we wanted to use this framework to also look at estimating parameters for that model, but using the uncertainty in the observations and cascading that uncertainty out to a risk profile for the decision makers. And so you're going to see a series of histograms here. The orange ones are the observations. So these are the data that we have observed in the field. These two are for flux measurements at these two different locations in the basin. And then these two are for hydraulic, just water levels at two different places in the model as well. And so the orange histograms represent the assumed uncertainty around those observations. And then the blue histograms are the model outputs from an ensemble of models. So we will sample a credible range around the parameters of the model, run the model, and that results in an ensemble of model outputs. Ideally, these two things should overlap. We should have correspondence between what the model says the water level is and what was observed in reality. This is often called model calibration, parameter estimation. And so when we start with the prior Monte Carlo, for the flux measurements, this isn't too bad. Those distributions are at least kind of touching. But we see a pretty distinct bias here in the hydraulic heads being too high. This is tens of feet too high. And in fact, if you look at the model, it's simulated as everywhere is flooded. And the reason for this was that we didn't have a good enough range for the prior information to actually cover the observations. This was due to kind of information that we got like from literature sources and a few direct measurements on the properties. We needed to expand those ranges to actually have more spread in the output and cover the data or the observations as we hoped we would. So once we expanded the bounds on the prior, you actually see now it's a wider distribution of model outputs, which is not great. We would like it to be more constrained, but it at least covers the data. And then if we finally perform history matching or parameter estimation, we get these pretty well into correspondence. You can see there are a few hundred measurements here. I won't lie, I picked a good one here. They don't all look this good, but this is exactly what we hoped for, where the ensemble of model outputs pretty much perfectly overlies the ensemble of uncertainty in the observations. In this case, we wanted these observations to be below the land surface. This was a hedge against flooding. And so the fact that these are not overlapping is okay. It's on the right side of the curve, on the correct side of the curve, which is what we wanted. So then we can create patterns of where the water is supplying these wells. And so here, these are kind of crazy looking patterns, I realize. And the reason that they're color floods is because by incorporating the uncertainty of the parameters in the model into this process, we can come up with a probabilistic map of these sources rather than just a single deterministic answer. These blue locations are pretty unlikely. What this is saying is in very few configurations of the model parameters, a particle that was simulated here got to one of these wells. It's pretty unlikely. In the yellow, where the probability is 100%, every model run assumed or simulated that particles that were at the surface would get to the well here. And so we provided this to the state, and they were pleased because they were supposed to have kind of a robustness measure around their results. So rather than drawing a line just at the 100% or this whole thing, they could make a decision somewhere in between to incorporate the uncertainty and decide how to handle the risk. So that's kind of like with a single model run, looking at how we incorporate the uncertainty of aspects of that single model. But what about the bigger system? What about sort of like crop suitability over the whole country with respect to climate change? And this is not my work, but I wanted to use it as an example, partly because that presidential commission asked a lot about this very question, which is, in the face of climate change, what will the growing season temperatures be in certain areas of the country, assuming a warming climate? And so on the left here, you can see this is just looking at, obviously, the United States. This yellow dot is, I forget exactly where, but it's in Iowa. It's a particular location in Iowa. And this is showing kind of current mean growing season temperature. But then on the right, you can see that there's a pretty significant increase. And you sort of see two patterns. Basically, the warmth is moving north. The warm, higher temperatures is moving north, which has two implications. It means that areas down here may get too hot to effectively grow crops. And areas in the north that were previously too cold may become suitable for crops. So I think of this as like a crop migration. But no parameters, simple parameters in one model about the water system wouldn't reflect this huge change. This is uncertainty in the forcings, in kind of the whole framework around the model. These researchers looked kind of at a global picture and kind of wanted to see, is there a change with a significant change with latitude of their modeled crop resilience? And so the black line in each of these, this is looking at 0 degrees, 60 degrees north, and 40 degrees south. So basically all the arable land going from the equator to the North Pole, or to the north and to the south. The dark line, the dark solid line here, is showing what would be the productivity at a 6-degree warming of 4 different crops, important crops: corn, soybeans, wheat, and rice. And then these kind of green shaded areas, the dark green, is showing places where there's actually a gain, right? So in some of these northern areas, you get more crop production, but all of these brown areas are decreases. So these are places where relative to kind of a baseline current condition, 6 degrees warming would mean a pretty dramatic decrease in crop productivity. But an important aspect of this is they assumed, the authors assumed irrigation for rice, but they did not assume irrigation for any of these other 3 crops. So this could be a huge driver for whether whether irrigation would be applied in these areas. And then that's a question for a hydrologic model, right? Kind of what I was showing before. We could start to look at what are the impacts of increasing irrigation in some of these areas. And so the drivers are not necessarily just the uncertainty within a single model. That's the point I'm trying to make. We need to look at the bigger picture outside of us. All right, so I started my career in environmental consulting, working for private consultancy, and we worked on some pretty small modeling projects. And typically, the result was a 3-ring binder. It was printed out. There was some tables, there were some nice pictures, and there was one outcome of a model, or even just data collection. And That was it. That was the product. That model never saw the light of day again. It just collected dust on a shelf. And I think that that's a disservice to the people that are trying to make decisions on natural resources. If we're doing modeling projects, we need to be thinking about how can we use that model to be tuned to a specific question and provide support for the real decisions. So that's the last part I'm going to talk about through two examples from my work. So one of these is a place called the Little Plover River in Wisconsin. So the Little Plover we're back to the Central Sands where we looked at the lakes before. And these black dots in the Central Sands are high capacity irrigation wells. So you can see that there's a huge number. This is actually a few years ago. There's a few more dots than there was back then. And if we look specifically at this small little base flow fed stream, this is the Little Plover River right here. And you can see it's surrounded by these dots. There's a lot of irrigation already in this area. And right now, legally or legislatively, the state of Wisconsin does not have a way to curtail existing pumping. If pumping has been allowed, there's really not a way to pull back. However, this particular river, the Little Plover River, has a mandated minimum flow. And this was based on historical conditions and looking at sort of trout habitat. There are trout in the stream, and sort of what are the minimum flows that would be suitable for the ecosystem. So there was a question about, can we use this information and use the model to come up with an optimal arrangement of pumping? If we had to make changes to what's allowed in the pumping, ignoring what's possible by law, but just on a technical side, would we be able to actually meet these needs in a systematic way? And looking at the hydrograph of the Little Plover River from the end of 2013 to the end of 2015, this is the time that we did this study, you can see that public rights flow, that flow level that's mandated, is violated quite a bit of the time. A lot of it is in so this one is in the winter, but especially like at the end of the irrigation season, there's a bit of a lag, and then there can be flow that dips below this level. And sometimes, quite alarmingly to some people, it actually has dried up completely in stretches. So we're in a situation where there's already, if you think about this from a basin management standpoint, there's probably too much irrigation allowed or allocated if you wanted to maintain the mandated flow in the stream. And so we can use the model in a couple different ways to evaluate how you might change that management. And one of the first important things to do is look at where when you pump water from a well, what is the source of that water? Is it diffuse flow from kind of the system around you, or is it actually coming at the expense of the stream? And this is well known for a long time to be a function largely of distance. So wells that are closer to the stream obtain most of the or more of the water that they pump at the expense of the stream than wells that are further away. But we can quantify this with the model. And we have this term called depletion potential. It's a fraction from zero, or a proportion from 0 to 1, where if the value is 1, that means that every liter that I remove from that well is accompanied by a decrease of a liter of flow in the stream. And if it's 0.1, that means for every liter that I pump from the well, only 1/10 of a liter of flow reduction happens in the stream, and the rest of it's coming from diffuse sources. And this very simple, well, I think, pretty simple plot here, showing that there's symmetry, right? That the depletion potential is highest near the river and drops off as you go away. But if you look at the capture zone of the river itself from a particle standpoint, like if you were looking at actual parcels of water, it's flowing from the north and then kind of ending up in here. That's what this pattern in the background is. And so it would give the impression that wells down here are not impacting the stream, that you would want to target wells that are in the path of the water that's actually flowing. And this was a complicated thing to talk with members of the legislature about, but it was very useful to be able to show there's no free pass. It's really a question of how close you are to the stream. So just these maps were very useful for decision support, but we wanted to take it further and say, in a hypothetical world, if you could curtail the pumping in the basin, how much and where would you need to reduce pumping to get the recovery of flow back into the river? And so we looked at different clusters of wells that had similar depletion potential for some technical reasons. And the first thing we did was allow any one of these wells to be reduced 100%. So if the algorithm suggested that you should absolutely terminate pumping in one well and get the concurrent recovery of water into the stream, that would be allowed by the algorithm. And this was the optimal arrangement of well decreases. And what do I mean by optimal? It's very specific. We wanted to minimize the amount of reduction, right? So we wanted to say, let's not cut flow if we don't have to from wells, but constrained to have the water level or the flow in the river at the mandated level. So there's too much pumping, the flow is too low. We want to find the optimal minimal amount of disruption to the pumping to get back to that flow level. Interestingly, these two wells here are actually city wells, and so there was a lot of hubbub and kind of controversy in the media about attacks on agriculture and sort of, vilifying farming. But really, the recommendation from this algorithm is that a lot of that flow would be made up by moving these two city wells. Nonetheless, this is kind of the arrangement that the algorithm determined, but this is allowing any well to go to 100% reduction. Now, clearly, if you reduce a well by 100%, if you basically turn it off, you're not going to be able to irrigate that field. One other possibility was, well, what if we could reduce only by 35%? Would that be better? Would that be a more efficient use of the resource? Because then you might be able to, if you're an irrigating grower, you might be able to find some savings in your irrigation. Maybe 35% is too much, but it's possible. So maybe that would be a possible threshold so that nobody would have to stop irrigating it completely, but it would spread the responsibility. And in fact, it does spread the responsibility in such a way that more wells are impacted, but to a lesser degree. The reductions are smaller. And this kind of got at some interesting questions, in my opinion, about fairness. Another question was, well, what if every single well was reduced the exact same amount? That would be fair in a way, but it would be way less efficient overall. If you look at this entire area and you would apply the same reduction to every well, in order to recover the flow, you'd need to reduce every well by 30%. If you allow this cap to be 35%, which is the panel on the left here, the actual total reduction in the whole system is only 26%. It's a little bit more efficient. And if you allow a few wells to go to zero, but a lot of other wells to be untouched, then it's actually the most efficient. But now you have questions of compensation and how could you compensate people that are being told they have to completely curtail their pumping. You can imagine this is very controversial and it's not something that was legally allowed at the moment, but from the technical side, this is a tool that, should the law change or should the goals of the basin, people in the basin, change, they could use this to find an optimal solution. All right, so I'm going to go into one more example of optimization, and this is looking at a contaminated site. So we're moving out to Long Island, New York. There's this place, a city called Bethpage, that's kind of right in here. And the U.S. Navy and what's now Northrop Grumman, at the time was Grumman Manufacturing, started manufacturing aircraft in the 1930s and really ramped up in World War II. So a lot of fighter jets. These are sort of the F-14 was one of the last jets that they manufactured. They started out with these kind of cartoon looking things. They also made things like the lunar excursion module for Apollo. So really, really kind of important place, but they've had a lot of, they spilled a lot of mostly degreasers, like trichloroethylene into the groundwater system in an area that supplies water for hundreds of thousands of people. And so there's been a long-term effort to clean this site up. It's still ongoing. And the current arrangement of the plume looks kind of like this. It's covering several miles in this direction. And then there's a complicated system of wells that are extracting contaminated water, treating it in treatment systems above ground, and then returning it to these green basins. And you can see the piping. This doesn't show the routing of the piping, but it shows that there's all kinds of different wells connected to these different injection points. And then these two are actually wells where they're injecting clean water deep back into the ground. And so we're working for the state of New York because they're kind of the middle ground between the Navy and Grumman, who are each responsible for aspects of this plume. And neither of them wants to be fully responsible because it costs a lot of money, of course. And so the state of New York is basically evaluating the effectiveness of this system and filling in gaps if there are gaps identified. And so we're working for the state in this case, but in collaboration with the Navy and Grumman and some others. And so one of the things that so we wanted to simulate the efficacy of this system by using a technique called particle tracking, where you basically tag a parcel of water simulated at each point in the system, and you can follow its trajectory through the model. And so every place that's gray here is, and it's actually in 3 dimensions, is a place where there is known contamination. So we tag a parcel in each model cell there and follow which well it goes to. Because what I'm not showing on this plot is there are actually public supply wells interspersed within this plume, which you'll see in a couple minutes. And so if we just look at the system at the baseline conditions, it's a little over 75% of the particles are captured by one well or another. However, we did a similar parameter estimation exercise as I showed for the Never Sink Basin earlier in the talk, where we have an ensemble. So really, we could have as little as maybe 73% capture and as high as about 77%. And you can use this as a metric of sort of the risk of action, right? If we want to be risk averse, when the model says, 75%, but we really assume maybe it's only 73%, let's favor solutions that are more conservative, that assume we're capturing less than we really are. One could also be risk tolerant and choose simulations that sort of overestimate from the mean. In this case, because this spread is not very big, the decision makers decided they wanted to stick with the kind of the risk neutral stance. So we basically selected the members of the ensemble that were closest to this median and then progressed into the optimization from there. So the previous exploration in the Little Plover had a single objective. The objective was to minimize the reduction in pumping to regain flow in the stream. Here we've got some competing objectives. One of them is, and actually, yeah, here I'll show you. So this is the plume outline. The red wells are the remediation wells that are pumping water out and treating it. The blue wells are actually water supply wells that are supplying the communities in the area. And so one very important metric or optimization goal is to minimize how much water is captured by the blue wells versus the red. So we want to make sure that these have to pump at a specified rate to supply their customers. So the red wells can be changed around to hopefully pull some of the plume closer to them and away from these blue wells. So that's one objective. Another objective is looking at the cost of the remediation. The more you pump for remediation, the more it will cost. And then a third objective is to minimize how much water gets to these down gradient wells, because these are water supply wells that have not yet been impacted by the plume. So we want to minimize how much water gets out of the current footprint and into these wells. And so we can actually look at all three of these objectives in one plot, where we've got water supply capture on the x-axis. So as we go further right, more water is getting captured by the blue water supply wells. And then if we look at remediation pumping as a percent of the baseline, 100% is kind of what they're pumping right now, but the optimization could increase the amount of pumping overall or decrease it as another objective. And these are kind of in competition. This is often called a Pareto frontier or a Pareto front. And the idea is out in the tails, decreasing the remediation pumping from this point to this point or this point doesn't really change the cost of the very much, but it has a really big impact on the water supply capture. Similarly, if we're on the limb of the curve over here, going up and down, going from 120% pumping to maybe 110% pumping, for example, maybe has very little difference in the water supply capture. But down in this curve, this is where changing one criterion has a big impact on the other. And there's this idea of Pareto optimality somewhere in here where the trade-off is equally injurious to both directions, and maybe it is one metric for what could be kind of the optimal trade-off, or sort of the best compromise between the two. And then in the color, we actually have the third objective, which is minimizing the down gradient capture. So the lighter color, kind of yellowish color, is showing less capture down gradient, and the darker color is higher. Note that there's very little difference. It's a small scale. And interestingly, all three of these objectives kind of converge around this point. There's kind of maybe a Pareto optimal point that serves all three of these reasonably well. However, the two that we wanted to explore were this one that's kind of the overall compromise, and then this one, which is the maximum remediation capture. So not worrying about the cost, but just what is the maximum remediation capture. And these changes are subtle because the situation is quite constrained. But if you kind of squint, you can see a few changes in the size of these red dots from the baseline pumping to the maximum remediation capture. And then if we look at the minimum down gradient capture, things are a little bit different. For example, we focus pumping over here as opposed to on the edge here, because they're really concerned about water getting through to these wells down here. And anything kind of going off to the east is less of a concern when the minimum down gradient is the bigger objective. But the point of all this is, it's one thing to try to find a compromise between competing objectives. It's another thing to be able to quantify those trade-offs. And that's what we're trying to do with the model here, using this multi-objective optimization framework. It's computationally expensive, but I think very powerful. And our conversations with the state, with the water utilities, and with the Navy and Grumman have been quite fruitful in this one. All right, so hopefully I've motivated that these three aspects of the future of water modeling resonate at least a little bit. But where do we go from here? Part of the charge for this lecture series, which I was really pleased to see, was how should people be thinking about what their research goals might be going forward into an uncertain future. And of course, that uncertain future is a lot driven by climate change. And the rhetoric on climate change can be pretty discouraging. It's pretty polarized, of course. I think we've all experienced this. But there was a paper in Nature just a couple of years ago that a member of the team pointed out in our conversation that I really wanted to share. What this is showing, these violin plots are showing how much people that were surveyed. There was a survey of a few thousand people in the United States, how much they think there is support for things like a carbon tax, citing renewable energy on public lands, moving to 100% renewable energy by 2035, the Green New Deal, which was kind of a suite of pretty aggressive climate actions that was proposed in the legislature, in the U.S. legislature, and then how worried people are about climate change, right? And so you can see that the median for these is often somewhere in the 35% range, always less than 50%, right? But at the same time, people were surveyed about what they actually believe, what their stance is, and that's these red lines. And what this is showing is, yes, the rhetoric is really negative, and there's a lot of discussion and kind of gloom and maybe a lack of desire for action on climate change. But in reality, most people, more people than we think, do want to see something happen and do want to take action. And so there's a divide here between the rhetoric and kind of the reality. And I just point this out to say that I think, you know, as we see more extreme events, as we experience kind of winters like this one and summers like the last, I think these things are all going to keep moving, and there's going to be a place for and there's always going to be a place for science and environmental modeling and engineering in this framework as the climate continues to change. But regardless of that, you know, I think most water, many or most water issues are local. And this was a really great quotation from a science article that another member of the team brought to my attention. And, you know, environmental governance depends on good, trustworthy information. We need models, we need good data. This is about the stocks, flows, and processes within resource systems being governed, as well as the human environment interactions. That's the integration piece, right? Affecting those systems. There's a place for us. There's a place for science and engineering and research. But importantly, this information must be congruent in scale with environmental events and decisions. And this is huge. This has been a tension within my agency. There's been a big push toward national level models, single models that are trying to simulate the whole United States at once. And then there's other models that are focused on much smaller scale. There's a place for all of it, but there's a danger if we lose the sense of scale, that highly aggregated information can ignore or average out local information that's actually important in identifying future problems and developing solutions. So I just want to kind of leave you with the idea that water modeling, using integrated systems, integrating with all the different aspects of decision space, and hopefully understanding risks and uncertainty along the way, will always have a role in decision support. And regardless of the rhetoric about climate change, things are changing. The systems are going to require us to get a handle on the water resources impacts or implications of those changes. And so there's a bright future for contributing to solving these issues, in my opinion. So thanks so much, and I'm happy to take any questions.
All right, thanks, Mike. Are there questions from the room? Yeah, or
Can you go back to where you did the optimization of the pivots in the first example?
Mm-hmm.
You were able to identify the pivots that could be turned off and had an effect. are you able to take those and then go with your best scenario and then increase the pumping at the ones that you didn't turn off and see what happened then?
That's a great question. Yeah, we didn't do that as part of this work, but you certainly could. And but that raises a really challenging problem. I worked on a similar project to this in Denmark with a graduate student, and one of the things that they allowed was exactly what I think what you're suggesting. Like, if you need to decrease pumping here, could you increase it over here, and maybe maybe put in a pipeline and still pump the same amount of water? The problem that they found, if you didn't constrain that too well, they found some of these wells would go up like 6-fold or 10-fold. And that's just impractical in terms of how much water is actually going to be able to be moved. The other really important factor of all of this is in the upper Midwest, in this kind of temperate environment, when you pump groundwater from the ground, it is coming at the expense of surface water somewhere, because the system is in equilibrium without the pumping. Water is entering as recharge, flowing through the ground, and leaving through a stream or entering a lake somewhere. And so as the distance from this stream increases, this well, for example, is probably getting most of its water at the expense of another stream. So there's no free lunch, right? At some point, you have to start to consider multiple places where you might be depleting. I hope that kind of answers your question.
There are some questions in chat here too, unless there's more questions from the room.
Okay.
Let's see, question from the chat. Do you have the updated groundwater map after the Southwest got the record level rains in the last year? How significantly did it actually change California's water access for things like agriculture?
That's a great question. No, I don't. And the maps that I was showing, those national maps, were actually from work that the New York Times did. And one of the challenges with groundwater data is that it's pretty distributed. There isn't really a federated system like there is with surface water, where the USGS, for example, collects a lot of the surface water flow data in the country. Groundwater data is very scattered. So the people at the New York Times had to make tons of phone calls to local agencies and things like that to get that big of a picture together. So I'm not sure what the last update is. Groundwater levels have recovered a little bit, and the reservoirs, the big charismatic reservoirs like the Lake Powell and Lake Mead have recovered a little bit, but it's kind of like a Band-Aid on a broken arm. It's given them a little bit of breathing room, which is really important, because the water regime in the Southwest is just fundamentally different now. And so there are renegotiations happening, and I don't know if people have read about this, but it's pretty stalled out. So having a little bit of breathing room is kind of lighting up those negotiations again. But the situation out there is still pretty dire. It's oversubscribed to a significant degree, and yeah, like something's probably going to have to change in water use at some point. I don't think a few wet years. It'll give a little bit of a reprieve here and there, but it's still, the trend is still pretty stark.
Yeah, let's see, some more questions pop up here. Let's see, did you use GoldSim for your modeling and Monte Carlo simulation?
Oh, good question. No, but we use a tool called PES++, which is it's developed largely in the groundwater world, but it's getting used. I'm actually working a lot with landscape modelers right now, but it's an open source and model independent framework for parameter estimation, uncertainty analysis, Monte Carlo type simulations and the optimization, the single and multiple objective optimization I showed. And so it's definitely yeah. So that's the framework that I've been working in. I've heard about GoldSim. I think it has some similar capabilities. I think it's a commercial product.
In your Central Wisconsin studies, what are the most significant data gaps?
Ooh, that's a great question. One of them is really getting handled right now with better coverage of like the Ameriflex towers and kind of eddy covariance to get after ET. One of the big questions and one of the sort of answers to concern about water levels that was kind of thrown as an alternative to agricultural pumping being chiefly responsible was pine trees. There are some pine plantations and some pine forests, and it's really there are pretty widely variable estimates of how much ET comes from the trees, and so that's been like just getting more direct measurements of ET will help us understand the water demand of both the crops and alternative land uses like forest. So that was probably the biggest data gap. Another, it would be nice to get after, I think, in some ways it would be nice to get after a little bit more accurate pumping information. Although in Wisconsin, the high capacity well users are compelled to self-report. Most of that reporting comes from electrical bills and pump capacity, so it's probably a little overestimated. It's pretty consistent throughout the state. Reporting compliance is really high, like 90% or more. So it's good data, but it would be nice to have a little bit more, probably more accurate and finer resolution in time data. Those are probably the biggest gaps.
Yeah. Hey, Mike. I've got a few questions for you here from a couple of people that have been messaging me as well.
Okay.
One question was, talk a lot about uncertainty in this presentation, and that's something we think about a lot, or we're trying to think more on as modelers, but oftentimes it's hard to convey that to stakeholders. And you talked a lot about that with the decision support. When you're analyzing uncertainty under the guise of understanding parameter estimation, do you tend to prefer to use algorithms to help you decide those parameter estimations, or or is there validity to also using different statistical measures to try to understand some of those parameter estimations?
I mean, I'm not sure I'd make a distinction. I mean, the algorithms that we're using are statistically based. I mean, it comes down to forms of regression. You know, like you come up with some kind of a loss function or an objective function that's based on concurrence between model outputs and observations of the state of what you're simulating, and you try to minimize that to a reasonable degree. And I say a reasonable degree because that's where the uncertainty comes in. We know the data aren't perfect, and we know that no matter how good our model is, it's also not perfect. So there is no magical set of parameters that will make perfect correspondence between the two. If we do get that, we're probably overfitting. And so that's kind of part of the challenge. And we use kind of a combination of Bayesian probability theory with regression to minimize those residuals, but acknowledging that this is a bit subjective, we decide how closely we want to make that correspondence be. And those are all different aspects of the uncertainty that come into it.
Okay, yeah, thanks. It sounds like it's a lot. There are many steps to teasing out that uncertainty. It's not just an application of an algorithm or just a statistical metric. There's a lot of juggling that has to be done between those. And one of the things I think you touched on too is that this is obviously, I loved the diagram of the water cycle and the discussion about it being integrated and not discrete buckets that we translate back and forth between. Each of those different processes has their own uncertainty attached to them. With the guise of what you're talking about as a whole, which are some of those parameters or some of those processes, more importantly, that have wider bounds of uncertainty that you're kind of interested in zooming in on more or understanding better?
Yeah. That's not an easy question to answer. I see what you're after. First I'll say, this isn't exactly an answer to your question. I'll get to it, but I'll just say that, you touched on, yes, all these different sources of information have uncertainty, and implicit in the idea of not considering the uncertainty of any of those processes is perfect knowledge, right? If we don't allow something to vary in our analysis, we are explicitly saying we know that perfectly. And the grand total of things that I can measure with perfect certainty in the natural environment is zero. There's nothing, right? Everything has at least some uncertainty. So we definitely try to bring that into the analysis. But which of those is the greatest? I think that's what you're really asking. Like, where could you put your effort to reduce the uncertainty the most? It really depends on the problem, and it depends on uncertainty is tricky in how you're describing it, because there are some things that can vary over a really big range, but don't actually impact the results very much. Like, one example is specific storage in groundwater. I find that in a lot of our problems, the storage is important to dial in the timing of things in a transient model, but we often have models that have what we call stress periods. So a time that, like, everything is considered to be steady. The temporal resolution might be a month. And so the changes in storage that get integrated over that month may kind of fall out into the ether. So then you can have a huge range. It looks really uncertain, right? But in reality, it's just that it's insensitive. It's just not really causing much impact. I think that the biggest factor often is really the biggest dials on the water balance overall, and those are either the precipitation, if it's a rainfall runoff model, or the recharge, which is an a derived product from the precipitation if it's groundwater, and the human use. If the human use is significant, it can really matter. And some of that comes down to that timing again. Actually, in that little plover model, it was really interesting because we had, monthly time stress periods, and we had a huge storm at the end of a month. All of the impact of that storm was experienced by the data in the next month. And so we actually had to transpose, like, we had to decrease the recharge in 1 month and increase it in the next month to make everything work, which seemed really goofy. But the point is that those big keys on how much water can either enter or leave the system, like spatially distributed, that's where I think the biggest impact is, and therefore I think the most uncertainty.
No, great, thanks, Mike. I do have one other question, if I can just ask one more. So I appreciate it, Mike. You had touched on in that last answer, kind of the temporal difference as well in some of these different processes that we're looking at. And so, kind of taking a spin on that temporal aspect, do you think that technology is advancing to the point where we can start considering real-time groundwater assessment modeling, particularly in advance of kind of these extreme drought situations? How could you kind of move to integrating these models and these dynamic picture in a closer to real time? How far away from that are we, you think?
I don't necessarily have a good answer for that. It's something I've been struggling with, and this is one of the places in surface water modeling where machine learning is and artificial intelligence is great, right? The ability to fit like an AI ML model to forecasts of flow at a gauge, at a single gauge, like the discharge in a stream, is uncanny. It's pretty amazing how well you can do, completely blowing off the physics. And if you can get that right, then yeah, if you get enough measurements of, say, the driver, which is then precipitation largely, or weather at least, you can make those forecasts really good. The groundwater system is tricky. It's diffuse and it's slow, and it's just poorly measured, even at the best. I mean, we have a lot of, in some places we can use geophysics to get a much higher resolution picture of the subsurface, but we still don't know that much. Like we're still having to infer a lot. And so I've dabbled in machine learning in groundwater systems a little bit, and it's been interesting, but it's been very difficult to be as specific. So I think that's a remaining big challenge. And I think there's a lot of hype, and maybe hype isn't the right word because that has a negative connotation. There's a lot of enthusiasm, I'll say, about machine learning for surface water systems, and people are throwing everything into that bucket, I feel like, and say, yeah, it'll solve all the problems. And I don't think that's quite accurate. I think we have to be very selective about which things we think we can make these more rapid, approximate, but maybe really great forecasts, and which things are not as suitable for that. And I think that's shaking out in the community a little bit as we go.
Great, thank you very much.
Mm-hmm.
Yeah. Mike, I do have a question. I like what you did with the integrated modeling of uncertainty analysis. So the final goal is provide decision support. So using the slide that you have now as example, so what the agency picked of these two scenarios for their final decision, and why they choose one over the other?
Yeah, that's a fantastic question. A subtlety to this particular case was that there was not a mechanism for the agency to change the pumping rates now, like a legal mechanism. So this was really at the end of the day, this was really more of an experiment or a proof of concept. However, I'll go back one. This image was used. This information was used by the regulators, and instead of using the optimization, because again they couldn't sort of mandate reductions of pumping widely throughout the basin, but using this information, they worked with the growers that were in these higher depletion potential wells, and using our model to actually come up with community solutions that would, for example, compensate this farmer for changing their practice. So several of these highly impactful farms just experienced that they converted them back to open space or wetlands in a couple cases. Also, those two city wells that I referred to down here, they don't look big here because the depletion potential isn't super high, but the pumping rate is super high. So actually the impact on the stream is disproportionately high. So this was actually, I would say, the more useful result in the end for the decision makers in this particular case. It's interesting because two things have happened. One, they probably have not reduced pumping in the basin enough to make the water level recover based on the modeling. However, it's rained a lot for several years in the last 4 years. I mean, the last year was a bit of a drought, but there's been a lot of water in central Wisconsin. So there's also a big perception that the problem is solved, and so there's less focus on it. The lakes that we were modeling that sometimes dry out, people are trying to get permits to pump water directly out of the lake over a ridge into a river to try to drop the water levels. So they're having the opposite problem right now.
How old are when did people start putting in these pivots? Like, how old is this practice here?
Yeah, I mean, it started like most places, I think, like basically the early 70s, but there was a pretty big explosion over the last 20 years. I'd say like about half of the wells are in the last 20 years. they're pretty maxed out. There's not much agricultural land in this region that could support irrigation that doesn't already. I mean, there were a few drought years, and there were some pretty big cost and tax incentives to buy pivots, so people kind of went for it. And the potatoes, you know, they grow other things, but the potatoes are it's very sandy soil, so it's perfect for irrigated potatoes. And they you know, Frito-Lay is the main client for this area, so like it's a lucrative crop. They make a lot of money there.
Okay, any other questions?
One more there.
Oh, I think we must one more online here. Let's see, what was the need for MO optimization using NSGA2? The goal is to determine the max remediation capture realization.
No, that's an excellent question. The idea was that was a little bit exploratory, and to be honest, at the end of the day, so, and this is maybe back to the how was the decision making used in this case. Realistically, this is it. This is the simulation that everybody could get behind, and the state and certainly the water utilities do not care about the cost. They are completely uninterested in how much the Navy and Grumman are going to pay. They went right to this number, and so from that standpoint, it wasn't necessarily required that we do the multi objectives. That's true, but there's that's one aspect. So we probably could have gotten away with a single objective of just this capture, but another aspect of this algorithm, the NSGA2 algorithm, is that there's a little more granularity in the fluctuations of the decision, what we call the decision variables. In other words, the pumping rates. And so you know, if we look at kind of this baseline pumping here, this is where they're all starting. And the sequential linear programming is the algorithm that we use for the single optimization or the single objective optimization. And it tends to jump to bounds of pumping. And so it'll like turn one well all the way on or all the way off. And then, you know, it's very it can be kind of coarse. And so even if you only use the single objective with the NSGA algorithm, it's a little bit more continuous. However, it's very expensive computationally. This little curve here required about 150,000 model runs. So, which were each I don't know, an hour, half an hour, something like that. So, luckily we have access to some heavy resources.
All right, well, I think that's all the questions. Well, thanks, Mike. That was excellent. Really enjoyed your talk.
Thank you. Thanks for having me. I appreciate it.
This is great. Oh, was that? Oh, yeah. I'll wave goodbye.
Like,
Wave goodbye.
He can only see Laura, so there's more.
Okay.
There are other people. There's a lot of people online.
Yeah, we had to get you after this talk.
Awesome. Great. Well, thanks for the interest. Appreciate it, and look forward to seeing you all in the future.
Sounds good.
Thank
Enjoy
you.
the rest of your day.
Thanks.
Thanks, Mike.